Welcome. This is the first video in a series related to finding and understanding the proof of the mean value theorem. This is part one. We're looking at Fermat's theorem about extreme values. Fermat's theorem about extreme values talks about a function who has a derivative everywhere, and we want to understand something about its extreme values. And here's the statement of one possible way of stating the Fermat's theorem. If a differentiable function f of x, so this means that f prime of x is defined everywhere, if this function has a local extreme at a particular point, so by a local extreme we mean that there's a maximum or a minimum at a point, at least in its neighborhood, then that means that the derivative at the point equals 0. This is the consequence. So here's a quick picture. If I were to think about a function and we have a point A, maybe it has a maximum, maybe my function has a minimum, those are my extremes. What we're saying is that if this function is differentiable, then the derivative must be 0 at the point. All right, our proof for this theorem starts with the following strategy. We're going to ask what happens if we have a derivative that's not equal to 0, and we're going to demonstrate that an extreme value, as shown above, is not possible. And what that means is that if I am at an extreme value, the only possibility is that the function's derivative equals 0, or maybe the function itself doesn't have a derivative, it's undifferentiable. An example of that would be a function where the maximum is at a point where it's not differentiable. Let's start our proof by taking a function that is differentiable, and we know that its derivative is not 0. And we'll start with an assumption that the derivative is actually positive. All right, what does a derivative mean? A derivative is defined by a limit as we take a slope between 2 points, and I'm going to use this definition where we take f of x minus f of a divided by x minus a. So that's a slope between 2 points, and we'll take a limit as x goes to a. So we have a limit, and in our assumption this limit is greater than 0. Now what that means is eventually, as x gets close enough to a, I'm going to be close to this value f prime of a. So eventually, for x close to a, the slope f of x minus f of a over x minus a is close to f prime, this number that represents the actual derivative. And in particular, because this is a positive number, there's space between that number and 0. And so we're going to look at a point where f of x minus f of a over x minus a must be greater than 1/2 of the actual derivative. And so this is some number, and we know it's positive as well. And we're going to look at this ratio, and it's going to tell me something about f of x compared to f of a. So we have two possibilities. I'm working on the left, or I'm working on the right. When I'm working on the left, I know that x is less than a. And that means that x minus a must be a negative. So it's some negative number. And in order for this quotient to be positive, which we know it is, this means that f of x minus f of a is also negative. And so if I solve for f of x, I discover f of x must be less than f of a. And so in a picture, what's happening is I've got my axes, here's my point A, here's my value f of a, and we know that when I'm close enough, so maybe some little interval here, just to the left of a, my function f of x has to stay below that point. We can't get above it. All right, so that's the left side. I can also talk about the right side, and so now let's talk about that. On the right side, we know x is greater than a, and so x minus a is positive. The denominator is positive, and the quotient's positive. This means f of x minus f of a must be positive. So f of x is greater than f of a. Okay, going back to our picture, what does that mean? It means on the other side, we know that my f of x is above this value. Okay? Strictly above, like not even or equal to. And so this means, and this is again on some little interval just to the right of a, so when x is close enough. Well, this picture means f of a must not be a maximum or a minimum. It's not an extreme. And so this is how we would prove Fermat's theorem. Well, how does this get used in practice? In practice, what we're doing is we're looking for extreme values, and in principle, a function is defined at so many points, uncountably infinitely many points. It would be hard to try to search for a maximum or a minimum by checking all the values. Fermat's theorem says if you know where f prime exists and you can find all the points where f prime does not equal 0, all of those points are automatically eliminated so that we can restrict our attention to points that need to be analyzed. So these points that we're going to analyze, these are points where f prime of x equals 0, and these are called our critical points of a function. And we'll talk more later in a separate video about how you analyze critical points. Our goal right now is just to find the critical points. So I've got a function f of x. It's a fourth power polynomial, and if I want to find where possible extreme values are, so we're going to find the critical points, and we do that by calculating the derivative. We get 4x cubed minus 6x, and we solve what are all the x values that make this formula, 4x cubed minus 6x, equal to 0. So this is the critical point equation, where we set the derivative equal to 0. And there's a common factor of 2x, leaving x squared minus 3. Two factors, 2x might be 0 or x squared minus 3 might be 0. The first factor leads to a critical value of 0. The second, I end up getting two critical values, plus and minus the square root of 3. So all points except these three cannot be extreme values. So the three possible critical values are 0, square root of 3, and negative square root of 3. So those are the only 3 points that might be extreme values. All the rest cannot be extremes. And that's one of the ways that we would use Fermat's theorem. It restricts the number of points we need to look at in order to find extreme values.